If you've ever stuck a magnet to a fridge, you've probably had one of two reactions. Either you didn't think about it at all because you were too busy reading a takeout menu, or you stood there for a second like, wait, how is this thing just gripping the fridge through nothing, with no wires, no batteries, no subscription service? And if you had that second reaction, congratulations. You just asked one of the most surprisingly deep questions in all of physics, and you did it while holding a pizza coupon. Because magnets are genuinely weird, not like, oh, that's neat, weird, more like this breaks my understanding of how objects should behave, weird. You have two pieces of metal, there's a gap of empty air between them, and one of them just decides to fly across that gap and slam into the other one. No one pushed it, no one pulled it, it just went. If a random object in your house started doing that, you would move. So let's actually figure out what's going on. And fair warning, the answer goes deeper than you'd expect from something you played with as a kid while sitting on a carpet in your pajamas. Magnets work because of moving electric charges, specifically tiny things happening inside atoms, at a scale so small that if an atom were the size of a football stadium, the nucleus would be a marble on the 50-yard line and you'd still be squinting. Every atom has electrons, and electrons, it turns out, have this property that makes each of them act like an absurdly small magnet. Part of that comes from the way they move around the atom, but part of it comes from something called spin, which is a quantum property, and before you click away, I promise this won't turn into a lecture. Spin doesn't mean the electron is literally spinning like a basketball on someone's finger. It just means the electron has a built-in magnetic personality. It was born that way. It didn't choose it. It didn't go through a phase. It's just always been magnetic. Now the key thing is this. In most atoms, electrons pair up in opposite directions. One points up, one points down, and they cancel each other out. It's like two people pulling a rope in opposite directions with the exact same strength. Nothing moves. The atom ends up magnetically boring. Which means most stuff around you, not magnetic, your desk, your shoes, your unfulfilled potential, magnetically neutral, all of it. This is actually the better question. Because if every single atom has electrons and every electron has a magnetic moment, shouldn't everything be at least a little magnetic? And technically, yes, everything does interact with magnetic fields a tiny bit. But in the overwhelming majority of materials, all those little magnetic contributions are pointed in random directions, canceling each other out so thoroughly that the net result is basically zero. Imagine a room full of people and everyone is yelling a different opinion at the same time. From outside, all you hear is noise. No single message gets through. That's what most materials are doing magnetically. Total chaos, no coordination, kind of like group projects in high school. So the real question isn't why do magnets work? It's why do some materials break the pattern and get organized? In certain special materials, iron, cobalt, nickel, and gadolinium, if you want to impress someone at a party where that kind of thing impresses people, something unusual happens. The electrons don't just randomly point wherever they want. They actually prefer to line up in the same direction as their neighbors. This is called ferromagnetism, and the best analogy I can give you is a stadium wave. 60,000 people in a stadium all just do whatever they want, stand up, sit down, check their phones, argue about the ref. You see nothing from the outside. It's just a mass of people. But if those same 60,000 people start standing and sitting in a coordinated pattern, suddenly you get this massive visible wave rolling around the entire stadium. A magnet is the atomic version of that. Billions of electrons all doing a coordinated wave, and from the outside you feel it as a magnetic field, one that can yank a paperclip off your desk from 2 inches away, which, when you think about it, is kind of terrifying for a force that's completely invisible. This is where things get a little spicy. If you think about it classically, magnets placed side by side should actually repel in some arrangements. So why would atoms voluntarily line up? Why would they cooperate? Atoms aren't known for their teamwork. The answer is quantum mechanics, specifically something called the exchange interaction, which is a fancy way of saying the rules of quantum physics make it so that in these specific materials, the lowest energy arrangement, the most stable, most comfortable state, is one where neighboring electron spins are aligned in the same direction. Think of it like this: it takes energy for them to point different ways. Pointing the same way is the lazy option, and atoms, much like me on a Sunday, will always choose the lazy option if physics lets them. So the electrons line up not because something forces them, but because it's literally the path of least resistance. Quantum mechanics said you can save energy by cooperating, and iron said say less. Now here's the thing nobody tells you. Even in a ferromagnetic material like iron, the whole object doesn't just snap into one giant perfect magnet automatically. That would be too easy, and physics hates easy. Instead, the material divides itself into regions called magnetic domains. Within each domain, millions of atomic magnets are beautifully aligned. Everyone's pointing the same way. It's organized, it's harmonious, it's lovely. But each domain might point in a completely different direction from the domain next to it. So one chunk of the iron is pointing left, another chunk is pointing up, another one is pointing at a 45-degree angle because it's feeling independent. From the outside, all those domains cancel each other out, and the whole piece of iron seems non-magnetic. It's like a choir where every section is singing a different song. Individually, each section sounds great. Together, it's a nightmare. This is why a random iron nail doesn't stick to your fridge. It's ferromagnetic, sure, but its domains are a mess. No one's in charge, there's no coordination. And this is the cool part, if you put that nail in a strong external magnetic field, the domains start to shift. Some rotate, some grow at the expense of their neighbors. Slowly, more and more domains align in the same direction, and once enough of them are pointing the same way, the nail becomes a magnet. In some materials, this alignment vanishes the moment you remove the external field. Those are soft magnets. In others, the alignment is stubborn, it stays. Those are permanent magnets, and those are the ones currently holding up your grocery list. You've heard of North Poles and South Poles, and you were probably told that opposite poles attract and like poles repel, and you accepted that and moved on. Fair. But what even are the poles? They're just the names we give to the two ends where the magnetic field is strongest outside the magnet. The field lines, those curvy arrows you've seen in textbooks, are drawn as leaving the North Pole and entering the South Pole, but they don't actually end at the South Pole. They keep going straight through the inside of the magnet and come back out the North Pole again. The lines are continuous loops. There is no starting point, there is no ending point. It's like a circular highway with no exits, just magnets all the way down. And this is why if you snap a magnet in half, hoping to get one piece that's just north and one piece that's just south, you'll be disappointed. Each half immediately becomes its own complete mini magnet with its own north and south pole. You didn't isolate a pole, you made two smaller magnets. Try it again and you'll get 4 magnets, then 8. At no point will you win this game. Physics has anticipated your move. Correct, and this surprises a lot of people. Magnets don't attract all metals. They strongly attract iron, nickel, cobalt, and certain alloys, but aluminum not magnetic, copper, nope, gold, silver, your fancy watch, none of them. Magnetism is not a general metal detector. It's extremely specific about which materials it wants to hang out with. It's picky, which is fair because honestly, if you were a fundamental force of nature, you'd be picky too. The reason comes back to how the electrons are arranged inside each material. If the electron configuration doesn't support that cooperative alignment we talked about, there's no ferromagnetism. End of story. Gold's electrons just aren't built for it. They're too busy being expensive. Here's where magnets go from fun fridge toy to backbone of modern civilization. Electricity and magnetism are not two separate things. They're two sides of the same coin. A moving electric charge creates a magnetic field. That means if you run current through a wire, that wire becomes magnetic. Wrap the wire into a coil and the field gets stronger and more focused. Stick a piece of iron inside that coil and the iron's domains align, turning the whole thing into a powerful electromagnet that you can switch on and off. This one idea that electricity and magnetism are connected basically runs the world. Electric motors, generators, speakers, MRI machines that take pictures of your brain, that thing at the scrapyard that lifts entire cars, doorbells, hard drives, all of it. Every single one relies on the fact that moving charges make magnetic fields and changing magnetic fields push charges around. It's one of the biggest unifications in the history of physics, eventually captured in Maxwell's equations, which are 4 equations that essentially say electricity and magnetism are dating and it's serious. Earth has its own magnetic field, that's why compasses work, but it's not because there's a giant bar magnet buried in the planet's core. That would be too simple, and again, physics is allergic to simple. Instead, Earth's magnetic field comes from electric currents generated by swirling molten iron in the outer core. It's basically a natural electromagnet powered by liquid metal convection, which sounds like something from a sci-fi movie, but it's just Tuesday for Earth. This has been useful to humans for centuries, long before anyone understood what magnetism even was. Ancient people discovered lodestone, a naturally magnetic mineral, and figured out it could point toward north. They didn't know about electrons or quantum spin. They just knew the rock was doing something helpful, and that was enough. Sort of magnets can lose their magnetism, and the main villain is heat. Remember how the whole magnet thing depends on domains staying aligned? Well, heat is just atoms vibrating faster. And if you heat a ferromagnetic material past a specific temperature called the Curie temperature, the thermal chaos overwhelms the magnetic order and the alignment falls apart. For iron, that happens around 770 degrees Celsius. Above that, it stops being ferromagnetic. The party's over. Everyone goes home. You can also weaken a magnet by hitting it hard enough. A physical shock can jostle the domains out of alignment, so if you've ever dropped a magnet and it seemed weaker afterward, it's not your imagination. You literally knocked the organization out of it. You demagnetized it with blunt force, which, honestly, is the most human way to solve a physics problem. So here it is, the complete answer. Magnets work because electrons have an intrinsic magnetic property. In most materials, those properties cancel. But in a few special materials, quantum mechanics says, actually line up, it's lower energy, and enough electrons comply that entire regions, domains, become magnetically aligned. Get enough of those domains pointing the same way, and the material generates a magnetic field strong enough to reach out into the space around it and pull things toward it. That field is what snaps the magnet to your fridge. It's what makes your compass point north. It's what spins the motor in your blender, and it all traces back to the quantum behavior of electrons and atoms. So the next time you see a magnet casually sticking to a refrigerator, just know you're looking at quantum mechanics with a grocery list pinned under it. That's kind of beautiful if you think about it. But also, you probably won't think about it because you'll be reading the takeout menu. And honestly, that's fine too.